Hey folks, in this video we will review some optimization techniques and look at applied optimization questions, that is, word problems that require us to do some optimization. So let's start off right with an example, and then we'll back up and see some of the fundamentals at work. Imagine we had this shape. It's a rectangle capped with a semicircle. We won't start with the optimization right away. Let's write down expressions for the area and the perimeter of this shape. Well, the area, it's a rectangle plus half of a circle. So the area of the rectangle is base times height. That's x times y. And the area of a circle is pi r squared, r the radius. But we want half of that, so we'll do half of pi x over 2 squared, x over 2. X halves is the radius of this semicircle. And for the perimeter, well, we don't quite have the full perimeter of that rectangle. We've got y, x, the base, and then y again. And then the circumference of half a circle, well, the circumference of a circle, 2 pi r, so half is half of 2 pi r. We'll put in that x over 2 again. And we can simplify. Now, the question at hand here is, if we require that the perimeter of this shape is 100 units, whenever we're measuring in, how can we maximize the area? What's the biggest the area could be? So let's start with that requirement that the perimeter is 100 units. And let's impose that. We have this expression for the perimeter. We'll set that equal to 100. And maybe it's not obvious right away, but what we'll do is we'll solve for y. Basically, in that case where the perimeter is 100, we'll figure out that y depends on x in this way. And now to come down to this area, we can write the formula we came up with earlier, which depended on both y and x. But now we can replace that y with this expression from the perimeter, specifically once we knew the perimeter was 100. So we'll plug that in here, and it's a bit of a mess, but we can factor a little bit and get a function for the area that depends only on x. And now this is an old problem. We've got a function of x. We want to maximize it. So we will look for a critical point. That is, we'll take the derivative, and the critical point is when that is equal to 0. We can solve and find that this happens when x is 50 over 1 plus pi fourths, which is about 28. And we can check this is actually a local max by doing the first derivative test. I won't show you the calculations to plug it in, but we could plug in a number larger than 28 and a number smaller than 28 into the first derivative to find their signs and see this is, yes, a local max. Maybe something even easier would be to take the second derivative. And I think you can verify the second derivative is negative, again, telling us it's a local max. But either way you do it, we found our maximum. When x is around 28 units, the area is maximized. Well, we have this expression for y in terms of x, so we could plug in about 28 into that to see that y then has to be around 14 units. And plug both of those into the area formula and see that the max of the area is about 700 square units. So let's review our optimization technique. And in both examples, we'll be thinking about the question of a global max and global min, if they exist. The first case is if we want to maximize and minimize a function on a closed interval. That is, we've got endpoints A and B that we're including in the interval. Well, in this case, we don't need to do any derivative tests. We'll find critical points because we may have local maxes or mins there, and then we'll also check the endpoints and then just compare all the outputs. That is, the value of the function at the endpoints versus the value of the function at the different critical points. So let's try an example. This function here, h of t, is t times e to the minus t on the interval 0 to 3. And the less than or equal signs here tell us we're including the endpoints. So this is a closed interval. We'll take the derivative. We'll set it equal to 0 so we can find the critical points. And we see there's a critical point when t is equal to 1. So now, and that's in the interval from 0 to 3, so it's worth checking. And now there's 3 places to check. The left side of our interval, the critical point we found on the inside, and the right side of our interval. We'll plug all of these into h, not into the derivative, into h to find the output of the function there. And we see that the lowest among them is at 0. And the highest among them is indeed at this critical point that we found. So we declare the first to be our global minimum and this critical point to be our global maximum. Now, if we don't have a closed interval, the unfortunate news is we may actually not have a global min or max or either. But the way that we'll approach this is we will start by looking for critical points. We'll classify them as maxes or mins, and when I say classify, I mean we'll use the first or second derivative test to do that. And then we can ask about what happens as we go off into the wings. That is, if this is an infinite interval, what happens when x gets very large, goes off to infinity, or very negative, goes off to minus infinity. So we'll see an example. Here's a function we may have seen on a worksheet. We can begin by looking for critical points. That is, we'll take the derivative of the function. We'll set it equal to 0. And we see there's a critical point when x is minus 1. So we saw in class that this is a local maximum. And then we can ask what happens away from that. Well, as x gets very, very large, the denominator of this fraction in the second term gets really small. In fact, the fraction will disappear, will vanish, go down to 0. So all we're left with is that 2 at the beginning. And then we can see that the same thing will happen as x goes to minus infinity. And I encourage you to look at the sign chart of the first derivatives to convince yourself that away from this critical point that we found at minus 1, the function is sort of going down both directions. That is, it's decreasing as x gets larger, but it was increasing up to that point. So it's really the peak of a sort of soul mountain. So x is going off to 2 as it gets large, or as it gets large in the minus direction. It never actually gets there. So we can't say there's a global minimum, but there is a global maximum at that one critical value we found. In the next video, we'll look at a couple examples of optimization questions.